What I want to talk about this lecture is twofold. First, I want to talk about um, the way different types are implemented. I mean, I just want to recap. We talked about the type systems. We talked about two different types of type systems. We talked about strong and weak. We talked about dynamic and static. I want to now talk about, first of all, how things are implemented actually behind the scenes. What choices do people who develop the language developers have when they decide how things are implemented. I will talk about how things are actually done in today's languages. Then I want to talk about a special type of type, which is pretty much the pointer and references type, and show behind the scenes how they are implemented. And then I want to talk about the purpose of types and the purpose of pointers. What are pointers really? What problems do we have with them? And how do we deal with those problems? That's pretty much our lecture for today. So let us begin. The first thing I want to talk about is how integers are implemented. So let's start talking about what are integers? What are they? Everybody knows that an integer is a number. But what it really is behind the scenes is really a word of memory, meaning that a word is allocated, and whatever the bits of that word, notice a word of memory is portrays, that's the number that we see. So it's not like other things where we're told, okay, we have this amount of exponent and this amount of base and whatever it is. It's just a word in memory. Now, that's a bit dated what I'm talking about. It used to be really a word memory. When we talked about 8-bit machines, it was actually a word. When we talked about 16-bit machines, so it was again a word, 2 bytes. When we came 32-bit machines, it remained a word. Notice how the size of the integer is increasing as we increase the word in memory. So we had 8-bit, 16-bit, 32-bit machines, and it was always an integer. So when you wrote int in a 16-bit machine, you got 16 bits, 2 bytes. When you wrote integer int on a 32-bit machine, you got 32 bits, 4 bytes, right? So an integer in a sense was a word of memory. That's what it was. And as computers became more sophisticated, and as computers grew, their memory size grew, and as the sizes of allocatable memory grew, meaning you were always able to allocate a word in memory. Okay, so as the size grew, you got more and more and more, and integers grew. So, for example, when I was a student on 16-bit machines, right? So we were asked what is the size of some kind of structure. So we always knew integer was 16 bits and the character was 8 bits, and this went on and on and on. But there was a shift in the way it was done when we moved over to 64-bit machines. In 64-bit machines, an integer is still only 32 bits. We need to say it's a half word. And in 64-bit machines, we are able to allocate half words, and therefore that is the 232-bit machine you can as well. But I'm just saying, but since we're able to allocate half words, so an integer is a half a word in memory, and that's the first time there's a major change from what was until 64-bit machines. Which means if you happen to come across code that was written for a 16-bit machine, you should understand what you're seeing. If you come across the same code written for 32-bit machines, you will see something else in memory. But when you come across the code in a 64-bit machine, we're still holding at 32 bits, which means that today integers got stuck in a sense at 32 bits, and they did not increase to 64 bits. This is a paradigm shift. And therefore, today when we ask you what is the size of an integer in memory, you should be saying 32 bits. Okay, so it's a half word. So there's a difference between what went on until 64-bit machines and 64-bit machines. Go know what's going to happen on 128-bit machines. But right now, this is what we're holding. 64-bit machines, and there's a difference between what was and what is. Okay? So integers, as I said, in a sense, is a half word. And that's the reason, by the way, when we started moving into code into 32-bit, into 64-bit, suddenly we started seeing things like int32 or int16 or that kind of business. Why you look at code that was written for 32-bit machines, you can sometimes see int16 or int32. What did the programmer mean to say? And the answer to that is that what he meant to say is, I want this to stay 32 bits, even if we move to the next platform. Could be the people who wrote that code did not know the next platform was going to stay 64 bits. History showed that it changes as memory changes. So people wrote int 16 or int 32 in order to tell the compiler, keep it at that size. Why do they care? So the answer is because it could very well be their algorithm is building upon some kind of manipulation of the bits. And therefore, it makes a very big difference. For example, they could be cycling through, they want to go back to the minus. Or they could, right, and they have an overflow and go back. Or they could be other reasons why they want the size not to change. And therefore, there was all these different types of integers that were inserted into code in order to offset this automatic change that went on between different versions of memory. So that pretty much is an integer. What is an enumeration? So an enumeration, in a sense, is just a way of representing some kind of ordered pair. It doesn't have to be an ordered set, sorry, an ordered set, not pair. An ordered set, meaning to say that there is, let's say we have an enumeration of days of the week, so we have a Tuesday, Wednesday, Thursday, right? It's an ordered set. There is an order to things. Wednesday comes before Thursday, which comes before Friday. Okay, so we're talking about some ordered set. We can ask, what is the third? We can ask, what is the fifth? We can ask, is Tuesday the third or the fourth? Okay, so notice we're talking about some kind of ordered set, which is what enumeration is. Now, behind the scenes, it can be implemented in different kind of ways. It can be implemented just as an integer, which is what C++ does, or C and its all its descendants. They just implement it as a way of mapping from some kind of um, um, string to some kind of number, of value. Value is better, right? So some kind of string, some kind of value. So if I go enumerate days of the week and I say Tuesday, Wednesday, Thursday, right? So Tuesday would be associated with some kind of value. So will be Wednesday, and so is Thursday. And if we start our week from Sunday, so we have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, etc. Right? So we could ask what is the first, and it will say 0, because 0 is the Sunday. We could tell it to start from some different number if we want. Tell it to start from 15, and then we'll have Sunday 15 and Monday 16 and Tuesday 17. Or we could just go give it every enumeration, every enum value, give it its own separate value if we want. And that's all it is just representing some kind of values. Notice it's not talking about some kind of ordered set, which is an interesting concept, because if we go and we say, and we give a value to everything, so we can ask, what is Monday times 3? And we get an answer that the answer is, in a sense, what is Monday times 3? So if Monday is 1, assuming Sunday is 0, so if Monday is 1, so Monday times 3 is 3, which is pretty much Wednesday, right? And so Monday times 3 is a Wednesday. And what is Friday plus 15? Well, it's just a number, right? That's 21, right? So in a sense, it's not representing an ordered set. It's just a way of, for us, the writers, to create some new type with these crazy values in it, whatever we want, makes no difference. But that is just an integer behind the scenes, and we could run any possible operator that runs with integers. We can run with an enumerator type. So we are not talking about an ordered set. But if some language gets up and says, I want to talk about enumeration as an ordered set, meaning to say that there is an order between Monday, Tuesday, and Wednesday. It's just not values. And you can't multiply Tuesday minus 5. It doesn't make sense. And neither does Wednesday times 15. That also doesn't make sense because the values as values have no meaning. The values as values are just there for us to run the system, but in a sense, they don't really have any real meaning. So the compiler might get up and say, listen, if you try to multiply Wednesday by 15, right, you don't get to March. It's just an error. It doesn't make sense. But if you want to ask me, what is the ordered number of Wednesday? The answer is 4, right? Or 3 if we start from 0. Or if you want to ask me, does Thursday come after Wednesday or before Friday? I can tell you yes, right? So I can talk about the relationship between the enumerated values. I could talk about the position of the enumerated value, but I can't talk about the enumerated value as a value. And there are languages that do that. For example, ADA does that, right? And there are other languages that do that. And they don't talk about numerated type as just a nice way of representing all kinds of integers, which is what C and its descendants do. So we have again two decisions. How do we want to relate to this enumeration type? Do we want this enumeration type to be a type that does just ordered set, or are we talking about some kind of numbers? The next type I want to talk about are Booleans. In a sense, what are Booleans? So Booleans obviously represent a true, false, or a one of two pick. Obviously, that's what they represent. And they can also be implemented in this time 3 different kind of ways. It could just be some kind of integer behind the scenes, like the C standard of 0 for false, anything else is true. And we have all the standard problems that we have with implementing things as integers. For example, what is true times 5? Well, true times 5 is true, usually. What about false times 3? Well, false times 3 should stay false. But what about true plus false? So you can interpret that as an or. Or how about false plus 5 somehow became true? So again, you can give that interpretation as false or 5. So that becomes true. Okay? So how about true minus true? True minus true became false somehow. Okay? So that's if we have all kinds of if we implement it as an integer. So that could be one way of implementing it. We can implement it using enumeration, which means that we can say, okay, let's enumerate Boolean, and we'll call the enumeration false true. Those are the values of the enumeration. So then we can ask, not what is the value of true, but whether it is true. Or is it, what is the order within the set? But again, it's not exact, it doesn't capture exactly, because you can ask, does false come before true? And the answer would be yes, even though as far as Boolean logic is concerned, it makes no sense. False does not come before true, okay? And true is not the second. So when we talk about a Boolean, you can implement it as a Boolean, as a enumeration. So that can also be done. And the third way of doing it is having it as a different type, which is the way it's done in newer languages. So if we go a bit back to the C-based languages, it's implemented as an integer. You can have it implemented, and then came the intermediate languages that implemented it as enumeration. And a lot of programmers in C and C++ in the beginning used to do that. Used to have some kind of header, and all the header had inside was like boolean.h, and all that it had inside was enumerate, boolean, false, true. Right, that's all it had inside. And they made it into enumeration. They made the code more readable and made the code more writable. Right? You couldn't have these crazy errors that some kind of mathematical equation kind of inside a conditional and not figure out why it's not working. You're supposed to write over something which is a boolean, and all these things that so they solved that problem, but it didn't solve all the other problems. And then you have the newer languages which pretty much have booleans as its own separate type. The next type I want to talk about are characters. So what are characters? Obviously, characters represent some kind of figure, which we the humans, are in a sense, um, give those figures all kind of interpretations, and every language has its own interpretation to all kind of different kind of figures, right? So we have this, I don't know, a cane, so that could be number 1 or 7, depending on your locale. Or if you have this duck, it could be number 2. And if you have this triangle, it could be the letter A, and all kind of other things like that. So we give all these symbols interpretation, and a character is just a way of, in a sense, representing that symbol. And the character, again, can be implemented in the same 3 different types. It could just be an integer, which again is the way it's done in the C-based languages, meaning character A and integer 65 are interchangeable. It's the same thing. You can ask yourself, what does A plus 5 equals, which is F, right? A plus 5 is an F, I believe, right? A plus 5 is an F. And you can ask yourself, what does F times 15 mean? So then there is no answer to that, no real answer. It's some kind of, I don't know what the ASCII table turns out to be, right? And and we're not talking about specifically, well, it's ordered, that little a comes before little b, because the ASCII table has them ordered, not because they're intrinsically ordered. So for example, capital Z is less than lowercase a, even though you might claim that doesn't make sense. You can claim that lowercase a should come before capital Z. But why is it like that? Because capital Z is some number like 70 something, right? Maybe 80 something. And lowercase a, right? 65 plus 26 gives us 81, 91, right? So that gives us, so that could be probably capital Z, probably 91. And lowercase a is a 97. So capital Z is ordered before lowercase a. You can claim that doesn't make sense. And you can say it's okay, it makes sense. So the order does not come from the programming language. The order comes from the fact that we all agree on some kind of representative table, which is the ASCII table, or UTF-8, right? So that's pretty much one way of representing characters. You can go and represent characters as enumeration. Now here it makes more sense, meaning you can enumerate all of the characters. We got A, B, C, D, or A, capital A, lowercase a, capital B, lowercase b. Enumerate them any way you think the order should be. And then we have everything ordered, meaning to say, does C come before, does little c come before capital T? The answer can be yes. It depends how you ordered them. Okay, so again, if you go and you adhere to the ASCII table, the answer will be no, because it's just an agreement that we should do it that way. But you could have done it differently as well. Now again, notice that the number 65 for A or 91 for Z, if we assume that Z is 91, doesn't really have any meaning. It's just the way we represent that figure or that symbol in our language. But if we put it in enumeration, so as I said, this is an ordered set. Well, characters are an ordered set. That's what they are, right? So there is an order. We have W, and then we have X, and then we have Y, and then we have Z. That is an order. You can ask, what is the 25th letter, and we get to answer Y. You can ask, what letter comes after E, and we will get F, right? You can ask, what is the position of, I don't know, F, and it will say, well, the position is 6, so it might say 5. So it'll say some kind of number like that, right? So notice it is an ordered pair, an ordered set, sorry. And therefore, enumeration could be a very classical way of actually implementing this, in all languages out there that do that. And then again, characters could be their own little type, have nothing to do with anything else. It's just a type, it's going to be other type, and implement it in that way. And this can go on and on for all different types. But the idea is to notice that there are different ways of actually implementing all these different types that we see and we learn to love, to learn to love. And we can go and say, okay, we'll do it this way, we can do it that way. And every one of the implementations obviously has some kind of advantage and disadvantage.